Okay, this is a interesting problem in terms of taking a look at putting two liquids in a tube and using the pressure from one liquid to lift up the other liquid a little bit. And so we have some pressure as a function of depth work to do here, and some working with how do we relate volumes and cylinders to each other, especially if they're different areas. The first part isn't too bad. If you take a look, they're going to put 100 grams of water in this cylinder, and they give you the area. And if we remember that the density of water is 100 grams per cubic centimeter, 100 grams per milliliter, we know that the 100 grams of water would have a volume of 100 cubic centimeters. And the volume of a cylinder is its area times its length. So if we want to know this length of this column or the height of this column of water, we can set the volume of water equal to its area times its length. So then we're simply solving for L, and we end up with our first answer of 16.7 centimeters. The second one's a little bit harder. Okay, remember what this column of water is doing. What we've got is we've got air pressure, which is going to be pushing down on the top, right? And we have this column of water, and so we'd like to know this pressure here at depth, because this pressure is what is helping to support this column of mercury. So one equation we're going to be able to write is for the pressure of water as a function of depth here. Another equation we could write is for this mercury, right? Because what this pressure of water is doing is supporting this height worth of mercury above this level. And so we also know that air pressure, since the tube is open, the air pressure is also pushing down here. So we know that the pressure of water is supporting the weight of this mercury, all right, and the air pressure, which is pushing down here. Now, later on, we're going to have to come back because what they want is little h, not this big H, and we'll have to do some other substitution work. But let's go ahead and get started on this one. All right, so we can write our first equation here in terms of all of our water knowledge, is that we've got P sub naught pushing down on the top, and that pressure is all supporting the pressure here due to the density, right, the gravity, and the height of the water column. That's just our regular pressure as a function of depth formula down at the bottom of the water. Okay, and again, that pressure in the water is also supporting this pressure, okay, plus from this column, density of the mercury, okay, G, and the height of that whole mercury column, right? That's a pressure as a function of depth formula for right here. Now, we know anytime we're at equal depths, we have to be at equal pressures, otherwise the fluids would be moving, all right? So that's how we know that the pressure here and the pressure here, okay, are equal to each other. So that gives us two equations to start with to relate the two columns. It's not exactly the little h yet that we're looking for, but it starts getting us closer towards that. So let's see what we can do. We set those equal to each other. We can see that the two air pressures will cancel out from each other, leaving us with this. And also G will cancel out, right, from the terms once we've subtracted off the P sub naughts. So that leaves us with a much simpler expression. We know the density of the water, we know the length of the water column, and we know the density of mercury. That's given in the problem as 13.6 grams per cubic centimeter. So we could solve for this big capital H here. But they want little h. All right, so let's take a look a little bit further. Let's look at another drawing. Come down here a bit. All right, so how can we express this height of the mercury right here, which is up above, which is more than what we need because they asked for this little h. Well, we can see from this height, right, and the little height that we're asking for, that we could express this larger height of mercury as both the sum of the little h here and of this part of this volume right here, which is H2. Okay, those heights are going to be equal. We can express it as that. So let's go ahead and substitute that expression in, and notice that we're getting closer to solving for the little h that we want to. However, it still leaves us with the height of this column. So here's what we need to realize about equal volumes. This red patch right here, okay, if we take a look, this red patch right here is, since this amount of water, okay, displaced a certain amount of mercury, that has to be equal to the volume of mercury that was lifted up, all right, before. So if you take a look, all right, as you added water here, and push the mercury down, that amount of mercury is what got pushed up. So what I'm kind of showing you, representing that, is that this red square, or this red cylinder, and this blue cylinder would be equal volumes towards each other. So what we can do is we can let H times A1, okay, equal H2 times A2. Or if we want to get rid of H2, so we leave everything in terms of H, we can solve for H2 in terms of H, and we know each of those areas. So then we're going to substitute this value in for H2. Then it's just it's algebra from there. So we do that, okay, we substitute in for our H2, A1 over A2, and then we can maybe start putting some numbers in at this point. We know that the density of the water is 1 gram per cubic centimeter. We knew its height. We solved for that in part A. We're given the density of the mercury, and then we can just combine these two terms and find out that that's 2.816 times H. And then it's just algebra from there on out. And if you solve that, we get the answer 0.435 centimeters. Okay? So the key to the problem was being able to realize that this little volume and this little volume are equal to each other, and how to substitute in for the right values. All right, there you go.